Hello folks, I'm Andrew, and wanted to put together a simple tutorial, and I want to stress simple tutorial, on using a bubble sextant for celestial navigation in an aircraft, and specifically for using the bubble sextant gauge that was created for Microsoft Flight Simulator by Dave Bitzer and Mark Beaumont, and then it was ported over to FSX by Chris Ogonowski. And this is going to be a simple tutorial. It's going to show how accessible this stuff is, and really anybody can use this thing. The disclaimer here is that if you are looking to learn to use a bubble sextant in an aircraft for real, and I'm not sure anyone actually does that these days, but if you were actually going to try that, this is not the tutorial for you. You probably die. Get real instruction. This is based on using the gauge in Microsoft Flight Simulator. That being said, the principles are the same, and that's what makes this gauge so much fun. You can really simulate classic styles of navigation using this great little gauge that Mr. Bitzer, Mr. Beaumont, and Mr. Ogonowski have created for us. I don't know any of those guys, but they really have given us a fun tool to play with in the sim here. So, we're sitting on the ground in Kona, Hawaii, and we'll go ahead and we'll take some example shots with the sextant, and then we'll plot the resulting lines of position in Google Earth. Before we do that, though, I do want to talk a little bit about some fundamentals of using a sextant, and we're not going to get into a lot of theory about how a sextant gives you the information it does. That information's out there if you want to study up yourself. I want to keep this simple, but there are definitely a few things that you need to keep in mind, and if you're brand new to this stuff, it's helpful to hear this before you start trying to use this gauge. So, the first thing is, well, really they all come down to the same thing. It's not a GPS, and there's three specific ways I want to talk about how it's not a GPS. First thing is, you're going to have to recalibrate your understanding of an acceptable standard of accuracy for navigation. You know, we're used to, in the GPS age here, we're all used to knowing our position in a matter of feet, and really single-digit feet if you have a good signal. With the sextant, we're talking more about a matter of miles. Single-digit miles if you've done everything right and you've gotten halfway lucky. Realistically, sextant's only going to tell you where you are within 5 or 10 miles. That would be considered a good fix with a sextant. With a bubble sextant, marine sextants are a little bit different, and because of that they're a little bit more accurate. A bubble sextant has more inherent inaccuracy built into it because of how it works. So we're looking for a level of accuracy of 5 to 10 miles, and if we can get that, we'll consider it good. And I know that that sounds just tragically bad compared to the accuracy we're all used to these days, but realistically, it's almost always good enough, you know? Assuming visibility's decent when you arrive at your destination, if you hit it within 5 or 10 miles, you'll find it. So, that's the first thing, though, you want to keep in mind. Definitely a different level of accuracy. The second principle of using a sextant that you need to keep in mind is that one sextant observation does not produce a position fix. You know, if I dropped you anywhere on the Earth's surface and gave you a GPS, all you'd have to do is glance at it and you would know immediately where you were. Sextant doesn't work that way. One sextant observation, or shot as they're called, one sextant shot doesn't give you a fix. It produces a line of position that you're on. If you've never heard that term, line of position, it may sound a little daunting, but I promise you, you already understand this concept. You may have probably just never heard it called that exactly. There are examples in aviation I could use, but let's keep it even simpler, okay? Anybody knows what a line of position is if you think of it like this. Let's say you're on a city street. You don't know where you are, but you do know you're on Smith Street. You have a map in your pocket of the city. You look at it and you see that Smith Street is a line on the map that runs from one side of the map to the other. You don't know where on Smith Street you are, and yet you do know that you're somewhere on that line. That's a line of position. Smith Street has become a line of position for you. So now you want to know exactly where you are on Smith Street. Well, you need a little more information, and let's pretend there's no addresses on the storefronts, and I don't know, it's post-apocalyptic. There's nobody to ask. The zombies don't come out till after it gets dark. Whatever. You're on your own here. How can you figure out exactly where you are if you only know you're on one line of position? Well, if you can find a second line of position, you can get a fix. So you start walking down the street until you hit a cross street, and you look at the sign, and it's Jones Street. So now you pull your map out, and you see that Jones Street is another street that runs from one end of the map to the other. The thing is, now you know you are simultaneously on Smith Street and Jones Street, and there's only one place you can possibly be if you're on two lines at the same time, and that is where they intersect. So you can look at your map, and now you can put your finger on the map and say, I am here at the intersection of Smith and Jones Street. Using a sextant to obtain a position fix is the same thing. You just need multiple lines of position. One sextant shot yields one line of position. If you can get more, you can fix your position. The third principle you want to keep in mind about a sextant is that, again, unlike a GPS, in our example, again, if I just dropped you somewhere on the Earth and you had no idea where you were, and I gave you a GPS, all you'd have to do is turn it on and it would tell you where it was. A sextant doesn't work that way. You need some preliminary information to use a sextant. It can't perform its job completely autonomously. And the information that you need is a rough idea of where you are before you start taking your sextant shots. This rough idea of where you are is called an assumed position, because you assume you're somewhere around there. Well, where do you get your assumed position from? Dead reckoning. To accurately and realistically use a sextant for navigation, you're going to have to dead reckon as well. And we're not going to get into anything about dead reckoning here. That is its own discipline. It's almost an art form. It's not complicated at all. It's very basic. But there's plenty of tutorials out there about dead reckoning, and if you need a primer on that, you can look up any of those other tutorials. I'm only making this one because, as far as I know, there aren't any videos out there on using this sextant, and I think maybe more people would use it if they saw how easy it was, really. So, those are the three basic things I want you to keep in mind as we start using the sextant here. Different standard of accuracy. One sextant shot only yields one line of position, and you need to start with a rough assumed position, and therefore dead reckoning is required. And I should have mentioned this, the assumed position really doesn't have to be that accurate. If you're within 100 or 200 miles of where you actually are, that's good enough for the sextant to do its job, and you'll end up with an idea within a few miles of where you are. So the assumed position doesn't have to be spot on, but it has to be a starting point. So, I was going to get into the basic theory of what a sextant does and talk about lines of equal elevation or circles of equal elevation and that sort of thing, and what a line of position from a sextant really is. You know what? That theory's out there. I'll put some links to some good references in the description if you want to learn more about this. Let's just stick with the nuts and bolts of how to use this thing to actually navigate in Microsoft Flight Simulator with it. So we'll start out, we'll take a couple example shots here, we'll plot our lines of position. I use Google Earth to plot lines of position and compare them to a course line. There's probably plenty of other tools out there that'll do it, but Google Earth is free, it's available to everybody, and it has all the tools we need. So I stick with that to keep it easy. So here's our setup. We are sitting on the ground on runway 35 here in Kona, Hawaii. It's a nice day, clear skies. I stuck us in the fantastic freeware C-47 by Manfred John and John Visser, and a really talented team of developers. If you like classic airplanes and you don't have this thing, you need to head over to Sim Outhouse and get this one. This is version 3.14 right here, and it's a Really fun airplane. Anyway, the Sextant goes well with it. So here is the Sextant. It's a 2D gauge. Once you install it, you can pop it up with a keyboard shortcut, or it's always available under Views, Instrument Panel, Sextant. Here we are in Google Earth. And here's Hawaii. Here's our actual aircraft position. I've put a pin on it right here. You can see that pin is sitting right on the runway 35 approach end at Kona. I dropped another pin over here. We'll use this for our assumed position when we start our sextant shots. And using the ruler tool, if I measure, well, wait a minute, we're on the circle here, we don't want that. Go to the line tool. If we measure, you can see that our assumed position is about 43, 44 miles away from our actual position. That'll yield some useful real-world shots. Before we start using the sextant, one thing I want to tell you, because it took me a while to figure out and it gave me fits. If you do decide to use Google Earth for this, there's one setting you might want to change. Go up here in Tools, Options, and under 3D View here, right down here under Terrain, this Elevation Exaggeration. 1.0 seems to be default. And this is a cool thing usually. What this does is when you zoom in, mountains start to look 3D, buildings start to look 3D. It's cool most of the time when you're using Google Earth, but when you're using Google Earth as a charting application, you want it to be a flat chart. You don't want any elevation exaggeration. You want to scale this down as small as you can, and if you set it at 0, it'll make it 0.01. The reason you want to do that is, if you don't, when you start drawing lines, they'll look like they match up. It'll look like the tail of one line will be on the beginning of another and that kind of thing, but as you zoom in and out and that elevation exaggeration starts to work, the lines will move around. It'll give you fits trying to line things up. So, turn that elevation exaggeration off. Now this thing behaves like a flat chart. It's a lot easier to plot on. Alright, with that being said, let's take our first shot. And if you look at the sextant here, this is basically a worksheet. You fill it out, you get down to the bottom, and then you click over here to take your shot. You see you've got a display of date and time, and you've got your Zulu time always available right here. That's relevant if you want to bring some realism to this and look up actual positions of celestial bodies that would be available to shoot, and you'll do that by referencing Zulu time. You always have to keep track of the time you took a fix when you're actually in a moving aircraft. First thing you'll do is enter your assumed position, latitude and longitude. Then you're going to enter the information about the star that you want to shoot. The azimuth is the direction in true degrees towards the star. The elevation is the elevation you expect the star to be above the horizon. Then you're going to click over here to start your sextant shot, and you're going to try to center a bouncing bubble on a bouncing star or sun if it's daytime. And when the shot completes, you'll have an observed elevation angle down here, and you'll get a distance offset in nautical miles. And we'll look at this is really the thing right here, the distance offset. That's the whole answer. That's what you need, and we'll look at how to use that. As far as what else the sextant does, there's a wheel over here. You can turn with your mouse scroll wheel. You'll notice it says bubble size 2. This changes the size of the bubble in the sextant, and 2 is that's the medium-sized bubble, and that seems to work the best. The controls over here are your elevation controls, coarse adjustment and fine adjustment. This over here, by the way, this is a chart that we'll use it, and I'll show you how it works and what you can do with it at the end of the 3 shots we're going to take. But I'll tell you right now, it's not as accurate as plotting the lines of position yourself on a chart like Google Earth. But if you just want something quick and dirty, this is a pretty useful tool. Alright, enough talking. Let's take a shot. And, okay, one more thing I'll tell you about this sextant. Unlike reality, this sextant gauge here, it does not care anything about which celestial bodies are where at any given time or what's visible. You can take a shot at any azimuth and any elevation, and it will return a useful result. Now if you want to add another level of realism to this, you can look up what would actually be available in the sky to shoot where you are on a given time and date, and just make your observations at those azimuths and those elevations. For instance, if you know that Antares is at a 130 degree azimuth, 36 degrees up, you can set that and shoot Antares. It simulates being forced to make do with what's available in the sky the way a real navigator would have. But you don't have to. You can take shots at any azimuth and elevation you want. And so for training purposes right now, that's what we're going to do. We're going to take a shot straight north. So the first thing we have to do is fill in our assumed position. And you notice I've got that over here on Google Earth. This is the pin we're going to use. Let's pull up the properties. And here's the latitude and longitude. So north 20 degrees, 7.71 minutes roughly. Now the first thing you're going to realize, and you set these with the mouse scroll wheel, so I'm going to scroll up 20 degrees north, 7.71 minutes. Well, my choices are 5 or 10. You have to round to the nearest 5 minutes. And that forces a certain level of inaccuracy into the shot, which results in a very real-world level of inaccuracy, because the tables that a real navigator would have to go to interpret the results of a sextant shot force him to round and interpolate through a bunch of steps, so there's always going to be some error involved. So the guys that created this gauge, they really did a good job simulating that. But the upshot is we need to round to the nearest 5 minutes. So 20 degrees, 7.7 minutes. I'd say 20 degrees, 10 minutes is probably the closest we can get. Now, longitude. Same thing, we're going to have to round. So 155 degrees, and obviously it'll be 25 minutes. Here's something important. You notice we're at a north latitude and we're at a west longitude. The numbers here do not include references to north or south, or east and west. Instead, they use positive and negative numbers. A positive latitude is in the northern hemisphere. A negative latitude is in the southern hemisphere. Longitude. A positive longitude is in the eastern hemisphere. A negative longitude is in the western hemisphere. Now, we're very definitely in the western hemisphere here in Hawaii. So 155, 25 degrees, that has to be negative. If you screw that up, the sextant, your assumed position is the other side of the globe. Way too far away for it to do you any good. This gauge is smart. It won't even let you take a shot unless your assumed position is within, I think it's 200 miles of where you're actually at. So if you ever set the sextant up and then it won't let you take a shot and you can't figure out why, that's probably why. Check your positive and negative values for latitude and longitude. So 155, 25 minutes. Negative, so scroll down. And you have to scroll down over here too. Alright, so 155, 25 minutes, that's west longitude because it's negative. Alright, now we set up the start position, which, like I said, for this example shot, we're just going to make that up. Azimuth, I want to shoot straight north, so 0 degrees, straight north. Elevation, we'll call it 35 degrees or so. We'll just make one up. Now the funny thing here is you set your azimuth just like we set our assumed position with the mouse scroll wheel over the number. You can't do that with the elevation. I'm scrolling my mouse right now and nothing's happening. If you want to set an elevation value, and you don't have to, but if you want to, and it can be useful in helping you interpret the results, you have to actually use these wheels over here, course elevation and fine elevation. So we'll set, I said 35 degrees, scroll up, 35 degrees, you'll notice I have choices of 34 or 36. This course elevation wheel adjusts in 2 degree jumps. So we'll call it 34 degrees, and then we're going to use the fine elevation wheel to adjust minutes, and when we get to 60 minutes, obviously we've jumped up to the next whole degree. So our sextant shot is all set up. We're going to shoot straight north on a 0 degree azimuth. We're going to shoot 35 degrees above the horizon. To take the shot, you just put your mouse over here in the middle of the eyepiece and you left click, and it'll start the shot. When it does, because this is daylight, what we're going to see is a green ball bouncing up and down in the viewfinder. This green ball simulates the sun with a safety filter on the lens of the sextant, which is how you take a sunshot with a sextant. You put a green filter over it so it doesn't blind you, obviously. So we're going to see this green ball bouncing up and down. Also bouncing up and down is going to be the bubble. That's going to be the sighting element of the sextant. Your job then becomes adjusting this fine elevation scroll wheel to, as best you can, center the bubble over the sun. You'll never get it centered, okay? The best you can do is average it out. So let's take a look. Start the shot. Okay, so the green thing's the sun. This is the bubble. The bubble's on average above the sun. We need to scroll down a little bit, so I'm going to go a few mouse clicks down here with the wheel. And you just want to play with it until the bubble averages out above and below the sextant, and it should, or I'm sorry, above and below the sun. You see it's spending about as much time below the sun as it is above the sun now, and when things aren't bouncing around, it actually centers up a little bit. So you can keep clicking up and down, or scrolling your mouse wheel up and down on this elevation, fine elevation wheel here, until you get it centered to the point where you're happy with it, and then you just let the shot complete. The shot runs for a minute, and I believe it averages things out over that minute. So if you have one setting for 30 seconds and then you change it, the sextant supposedly will take that into account. I'm pretty happy with that. I'm just going to leave it alone and let the shot complete. And when it completes, this visual disappears. There you go, it just completed. And we have a returned value, okay? We have a distance offset in miles, and it's negative 25 miles. That's really the critical value that the sextant shot gave us. From that information, we can plot our LOP, our line of position. So here's how we're going to do that. We're going to go to our chart, which is Google Earth. We're going to start at our assumed position, and we're going to measure 25 miles off of that assumed position. The distance is negative, so we're going to measure 25 miles away from the star, or the sun, or whatever it was we shot. The sun wouldn't be due north of you in Hawaii, I guess, but that's what we shot, so we'll call it a star. Now, since we shot due north, and the distance is negative, we want to measure 25 miles south. And this is why I recommend setting an elevation even though you don't need to. If you forget whether you're supposed to move toward the star or away from the star based on a positive or negative distance offset, comparing the expected elevation with the measured elevation will help you figure that out. We expected our star to be 35 degrees above the horizon when we took this shot. What we see is that we measured the star to be 34 degrees and 35 minutes above the horizon. We measured the star to be lower than we expected it to be. Now think about that. The closer you are to a star, the higher it appears in the sky, right? The farther away, the lower it appears toward the horizon. Since we measured the star at a lower angle than we expected it to be, we know we must be farther away from the star than we thought we were. So we're going to measure 25 miles away from the azimuth. And since the azimuth was straight north, we're going to measure 25 miles south. So we're going to grab the ruler tool. Okay, make sure you're measuring nautical miles. We're going to click a line on assumed position here. And we're going to drag a line out 25 miles to the south. And you'll notice that in the ruler box here, you've got a ground length and map length. They'll be the same. That's your line length, okay? And then your heading. So we want to go straight south for 25 miles. And, you know, how precise do you have to get it? Not very, obviously. We're within a couple hundredths of a mile here at this point, and a degree, so that's probably plenty good enough. Alright, so I'm going to click to anchor that line right there. Okay. So that's our distance offset. But now what we need to do to actually, that's not a line of position, okay? Lines of position are always perpendicular to the azimuth. This just was our distance offset from the assumed position down to the line of position we're actually on, is down here. But now to make that line of position, we actually need a line of position that's perpendicular to the azimuth, so 90 degrees off of the azimuth, running through here. Well, I used an azimuth that was straight north, correct? So if the azimuth's straight north, what's perpendicular to that? East and west, right? So we need an east and west line running right through this point. Now we could just drop a pin here and then start a whole new line and draw an east-west line through there. But easiest way to do this in Google Earth, you'll notice each one of these ends of this line are a handle. I can grab, we'll leave that one where it is because that's what we just measured to. I'll just grab this handle over here and I'll rotate and I'll drag, and we're going to drag an east-west line. Now look at the heading box in the ruler box up there. We want a 90-degree heading. And that heading box is kind of funny. Sometimes it indicates one direction, sometimes it indicates the reciprocal, so you'll have to think about that sometimes. But we know that 090 is an east-west line, so there we go. Alright? And you can make this line as long as you want, because what you know now is you're somewhere on this line. That is your line of position, and you're somewhere on it. But you could be way over here, you could be way over here, you don't know. So you make that line as long as you feel like you practically need to. If you save it, it won't go away. I like to make it green, just because that's what I always make celestial LOPs. Okay? So, that is our first line of position. We know we're roughly somewhere on this line. So let's compare at this point. Does it pass through our actual position? Pretty close, remember. Sextant. It's not a GPS. It's not going to be super accurate. But let's see how far off we are. Look at that. We're only 0.6 of a mile away from our assumed position. Pretty good. But it's only one LOP. There are times when one LOP is all you need for a ground speed check, that kind of thing. But right now we're shooting for a fix. We want to see how closely to reality we can fix our position. So we have one east-west line of position. Ideally, if you're going to cross two lines of position, you want them as near to right angles as you can. That'll be your most precise fix. So since we shot a star due north for an east-west line of position, let's shoot a star due east, and we'll get a north-south line of position. So, back to our sextant. Oh, one thing I forgot to do. Since we've completed our first shot, I'm going to click the star 1 button over here. And you'll see a line is drawn on this chart. We'll come back to how to use that line later. I just didn't want to forget to do it. So now, we're going to clear our sextant and get ready for the next reading. The way you do that is you click the center of it, and that'll clear it. And let's set up for our next shot. We're still at the same assumed position, but this time we want to shoot at an azimuth of 90 degrees, due east. This will give us a north-south line of position. 90 degrees. And again, the elevation doesn't matter, but we'll set one, alright? 41 degrees, great. Click to start the shot. And adjust the fine elevation wheel here to bring the bubble as close to centered over the star as we can. And this thing's showing a green sun because it's daylight. The gauge is smart. If it's dark, if it's nighttime, you'll actually see a field of stars, with one star being obviously larger than the others, and that's the one you're trying to center. Works exactly the same way. I'd say that is just about averaged out right. Pretty close. We'll just let the shot complete. And you can stop the shot early by clicking the viewfinder again, but you're going to get more accuracy by letting it average it out that full minute. So, alright, it's completed. We got our new distance offset here. Before I forget, let's click the star 2 button, draw a second line. Now, back over here, distance offset, 35 miles. Again, it's negative, which means we have to measure away from our azimuth from our assumed position. So we're going to measure 35 miles due west of our assumed position this time. And again, if you forget whether a negative distance means toward or away from, let's compare our expected elevation to our measured elevation. We expected that star to be 41 degrees above the horizon. We measured it at 40 degrees in 25 minutes. We measured it lower than what we expected, which means we are further away from it than we expected. Since towards the star is 90 degrees, we need to measure 35 degrees away from the star. So we're going to measure west. 35 degrees, I'm sorry, 35 miles. We need to measure 35 nautical miles due west. So again, looking at the values up there in that ruler box, we look for a line that's 35 miles long due west. So we'll adjust it. Due west, 35 miles. I'd say that's pretty good right there. Click to anchor. Now, again, that was just measuring the offset from our assumed position. To draw our actual line of position, lines of position are always perpendicular to the azimuth of the star, right? We shot the star at an azimuth of 090, due east. That means our line of position has to run perpendicular to that, which is north and south, right? So we need to make a north-south line here. So we'll grab the other handle of this line and just pivot it around that place we marked. And we can draw, a nice long line here, okay? The key is just that this line runs north-south. So if you look at the heading in the ruler box there, it's going to show me a north heading. Sometimes it'll show you north, sometimes it'll show you south. It's unpredictable, so you'll have to be ready to come up with the reciprocal of whatever you're drawing. But north and south is pretty easy. We know we want a 0-degree line, so that's roughly good. We'll save it. Again, we'll turn it green. Alright, now these are two lines of position. We know we are simultaneously on this line, somewhere, anywhere on this line, but we're also on this line at the same time. And there's only one place we can be on both lines at the same time, right? That's where they cross. So that is where the sextant tells us our position is. Is it exactly where we are? No. Is it pretty darn close? Yeah, it is. Let's see how far off we are. Roughly 1 mile. We are 1 mile off. Like I said, if you can fix your position using the sextant within 5 or 10 miles, you're doing good. So that's a completely acceptable shot right there, or fix. Usually, the most accurate fix you can get is from 3 lines of position. So why don't we take one more shot, plot one more line of position, and see if it helps us out or not. Since we've already got 2 lines that are at right angles to each other, ideally we'd like one running kind of through the middle, right? So let's take a shot that's about 45 degrees off of this, okay? So let's take a shot with an azimuth of 45 degrees this time. That'll be right between the two. And elevation, again, doesn't matter, but we'll shoot 51 degrees up. First click of the viewfinder will reset everything. Alright, now it's ready for the new shot at a 45 degree azimuth. The assumed position hasn't changed, it's still set. And here comes the third shot. Going to use our mouse scroll wheel to adjust this to get that sun centered up best we can. I'll show you what happens if you change the bubble size too while we're waiting. See, there's the largest bubble you can get. There's the smallest bubble you can get. Seems like the medium-sized bubble, bubble 2, is the best compromise here. Yeah, I'd say that's pretty close. just let it complete. Alright, so we got a distance offset of 45 miles. Once again, it's negative, which means we need to go to our chart and measure 45 nautical miles away from our azimuth. Negative value means measure away from your azimuth. And again, it makes sense, right? Expected elevation, measured elevation. Measured elevation lower than expected elevation, meaning we are farther away from the star. So, we need to measure 45 degrees away from the assumed position on the reciprocal of the azimuth. So, what's the reciprocal of 45? 225. So 45 degrees on a 225 course. I'm sorry, 45 miles on a 225 course. 45 miles. 45 miles. 45 miles on a 225 course. 45 miles on a 225 course. About right there. We'll anchor. Okay. Now, our line of position is going to be perpendicular to this, correct? So, we need to pivot this line perpendicular to our azimuth. So if our azimuth was 45 degrees, or 225 degrees away, our azimuth was 45 degrees, we measured 225 degrees away, so we need the reciprocal of that, okay? So we'll swing it about 90 degrees visually, and let's look at our heading, alright? We were at 225, so 90 degrees off of that would be 135, since that's how it's going to show us this thing. And we will measure about 135. We don't have to make the line very long because we know it's near where it crosses the other two. About right there. Okay, so now you see we have triangle. Theoretically, we would be near the middle of this triangle. In this particular case, I think that may have actually given us a little bit more error than we had before. When we were just using a two-line fix, we were only 1 mile off. If I measure to the center of the triangle, we're 1.7 miles off. Most of the time, you will be within that triangle, and you can take as your fix the center of the triangle. In this particular case, didn't quite work out. Again, bubble sextant, not the most accurate thing. But look, we know where we are within an accuracy of less than 2 miles. Pretty good. So I'll leave those 3 lines there. The last thing I want to show you is how to use this chart over here, if you choose to. You don't even need to, but if you want to, after every shot you take, you need to click the *1 button, *2 button, or *3 button to draw a line. So you can see I've already drawn *1 and *2. We've taken shot number 3. Let's click *3 button, and we'll get one more line. Now you'll see that these 3 lines cross, and they don't really indicate a triangle. It looks like they cross perfectly on here. We can zoom in on Google Earth a lot more than you can on this chart. You can't zoom in at all, so the accuracy level on Google Earth is much higher. But for a quick look, what this is telling us here is the center of the chart, this green bubble, is our assumed position. 20 degrees, 10 minutes north, minus 155, minus 25. That's a west longitude. So that's our assumed position. This is where we measure our actual position to be. And you'll notice it's, if this line down here is 60 miles south, the midpoint's 30 miles south, so it's about 25 miles south of the assumed position and, about 30 miles west, which, yes, is roughly where we are. But even easier than measuring distances like that is you can just move this green bubble, and as you do, the latitude and longitude it indicates will change. You can't click it and drag it. That's something I've tried to do every time I've tried to use this, and if you click this, as the tooltip says, it'll actually close the sextant. So don't click it. Use these arrows, green arrows, and click, 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 click. You can move that green circle down, and then left arrow, click, click, click. Put it right where all those lines converge. Now, of course, you can't get it dead on. You could only have so much precision because each click moves it a certain amount. But we'll call it right there. And then you can read your latitude and longitude, and theoretically that's a rough fix. So let's plot this. 19 degrees, 50 minutes north. We'll just throw a new point on here and see what happens. 19 degrees and 50 minutes north. Alright, and 155, 57 degrees west. 155 and 57.0 degrees west. Let's see where that ends up. Okay. So, it's way up here. If we measure how far from our actual position that is, yeah, 8.5 miles off. Now, that's still not bad. Like I said, as long as you're within 5 or 10 miles, that's about what you can expect out of a sextant. So, a quick and dirty fix 8.5 miles away is still not too bad. But you can see that actually plotting our lines of position on the chart, like a real navigator would, gives us a much closer idea, within a mile or mile and a half of where we are. So, plotting the lines of position is going to be more accurate. But it is nice that they included this chart, and for a quick and dirty check on your position, yeah, it's absolutely useful. Alright. You know, I was going to change it to night and take some shots at night, but to be honest, all that does is change the view in the viewfinder. I don't think you need to see that. But I did tell you that I would talk a little bit about the added level of realism of using celestial bodies that would actually be available at your location at the time and date that you're there. If you want to do this the way a real navigator would have, a good part of the preliminary work here is figuring out what you can shoot in the first place. Now, I think it's obvious that you have a lot more potential targets to shoot at night because there's stars out, right? During the day, all you have is the sun, and sometimes you do have the moon. Sometimes the moon's visible. I've noticed the moon's never really visible during the day in the sim, but in reality, we all know the moon's up during the day about half the time. So if you happen to be lucky, during the day you have two things you can shoot, but at night, boy, you've got a lot of options. A common technique when you're planning long flights where you're relying on celestial navigation is to shoot, or is to take off and fly most of the flight at night, but time your arrival an hour or two before sunrise, so you can actually pick up a line of position that passes through your destination and fly it into your destination. Won't really get into those kinds of techniques right now. That's maybe a little advanced for just this quick tutorial, but I do want to show you, if I can find it. There we go. These are a couple flights that I've done using the Sextant, okay? The first shot from Honolulu down to Johnston Atoll. I flew it during the day, and so you'll notice that at every dead reckoning checkpoint, when I took a shot, I took it off the sun. You'll notice how the angles of the lines of position change over time. That's because, naturally, the angle of the sun in regards to my aircraft was changing over time. I actually looked up what it would be and took a shot at the proper azimuth. And so these lines of position are exactly what a navigator in a real aircraft would have ended up with for this flight at that time of day. And the technique here, I did use a landfall technique of dead reckoning to a point somewhere north of Johnston Atoll, and then pre-calculating that I would arrive around a certain time period. And at that time, I went to the astronomical almanac, which I'm going to show you here in a minute, and looked up what the line of position from the sun would be that passed through Johnston Atoll at that time, picked it up, and flew it into Johnston Atoll, and worked out just fine. The second flight I've done is I flew from Johnston Atoll down to Kiribati here in the Line Islands. This is Christmas Island and Cassidy International Airport. I flew this flight at night, but I got there about an hour after sunrise, so again I could pick up a line of position and fly it into the island. And so look at my shots on this one. Notice I got a fix here, and I got a fix here. I got a 2-shot fix here, but I only have one line of position here for the first checkpoint. Now this is technique only, and the more you read about this and play with it, the more you'll figure out what you want to do. But I was only about 40 minutes out of Johnston Atoll at this point. I know it says 1 hour fix. It's because I planned it to fly in a slower airplane, then chose a faster one instead, so I got there quicker. So I wasn't very far at this point. I knew I hadn't drifted very far, of course. I just wanted a quick check on ground speed at this point. So I chose one star to shoot that was directly in front of the airplane, which yielded a line of position darn near 90 degrees to my course line, right? Okay, granted, if the star had been directly in front of my airplane, it would have been a perfect 90-degree line of position. It was the closest star I could find to being in front of my airplane, but it yielded a nice, sharp, almost perpendicular line of position. It was an excellent ground speed check. After fix 2, I took shots off of 2 stars. I took one off of a star that was nearly in front of me, and I got another ground speed line. The line of position being almost perpendicular to my course. Then I shot a star that was somewhere off my wing. I think it was somewhere off my left wing. And what that yields is a line of position that's almost parallel to your course line. And so that's considered a course shot. When you shoot a star in front of you or behind you, you get a line of position that's most useful for checking ground speed. That's a speed shot. When you shoot a line off, or you shoot a star off your wing, you get a line of position that's most useful for checking course. So at this point I saw that I was fast, and I'd started drifting left of course. I didn't put any corrections in. I figured I'd give it one more check. Here at fix 3, I took a good 3-star fix. Figure I'm somewhere right in the middle there. I'm obviously fast and left of course. I started introducing corrections. So, anyhow, guess I got off on a little tangent there, just talking about how and why you might want to choose stars at different angles to your aircraft, depending on the kind of line of position you want. Now, let's talk about where to get those stars, okay? And that is this website right here. I'll throw it in the description. It's run by the U.S. Naval Observatory, and this is for the purpose of celestial navigation. Yeah, some people still do this stuff. Typically they're mariners these days, and typically they're recreational sailors. And of course everybody has GPS these days, but recreational mariners do not have backup IRS units in their aircraft. So if the GPS system were ever to go down, boy, they'd be lost out there in the ocean. Well, most of them still carry sextants and practice celestial navigation as a backup, because it's the only backup you've got out there. So that's why the U.S. Naval Observatory publishes the Almanac here. And what you'll see is you can enter any date you want. Now the date I happen to have us in the sim right now is June 1st, 2016. So let's look up a time before dawn here. And let me think for a minute. What time is it in Hawaii? 2 hours earlier, so yeah, so about 10:30 Zulu will be sometime in the early morning. Alright, and you have to enter your assumed position. So what do we have here for an assumed position? What were we using? 20 degrees, 7.7 north. And west, 155, 24.8. Alright, get data. Alright, and this is celestial navigation data for 2016 June 1 at 10:30 UTC for this assumed position. So, here's what's visible. Planets, the sun and the moon, always go up here on top in red. That's just how they do it. The brighter stars that are more typically used for navigation are in blue. The dimmer stars are in black. And I'm not sure why Polaris and Aries are down here in green. There must be something special about them. Well, I mean, we know what Polaris is, obviously. I'm not sure why Aries is down here, other than it's the base measurement of Greenwich hour angle, which is this this GHA here stands for Greenwich hour angle Aries, and then this is the offset from the GHA of Aries. Or, well, this isn't the offset, but there's a table. You don't have to use any of that for the Sextant gauge. Okay, it does all that magic for you. There's a lot of behind-the-scenes work in tables to arrive at that distance offset that the Sextant ultimately delivers for you. And this gauge does it for you, so you don't need to worry about what I'm babbling about right now. The columns you're interested in here, okay, are ZN, which is Azmuth. It's easy to think of it as zenith, but it's not. It's azimuth. So that's the direction to the heavenly body. So if you want to shoot Mars, for instance, here, okay, you're going to shoot 202 degrees, and HC is expected altitude, expected elevation. So you're going to shoot 45 degrees, 22 minutes up. So azimuth is 202, elevation 45 degrees, 22 minutes. That's where you take your shot. So, if you're flying, I don't know, let's say you're flying east right now, okay? And let's say you want a shot that gives you a ground speed check. We talked about in that case you want to shoot something that's in front of you or behind you to get a line that's perpendicular to your course. So if your course line is east-west, you want a north-south line of position, that means you need to shoot something with an east or west azimuth to get a north or south line of position, right? So, let's see here. Well, Jupiter's almost due west of us, so if we're in an aircraft that, relies on celestial navigation, there's a little Astrodome you can climb up in, and you can get a 360-degree view of the horizon. So we could shoot Jupiter, even though it's behind us. What else could we shoot here? Altair is only 97 degrees. That's not too bad. That'd yield an almost perpendicular line of position. Enif, 85.9 degrees. Well, and so on. We could shoot any of those and get a roughly north-south line of position, right? Now let's say we're flying east, and we want an east-west line of position for a course check. Well, that means if we want an east-west line of position, we need a star that's to our north or our south, right? Because lines of position are always perpendicular to the azimuth. So let's look for an azimuth that's north or south. Well, here we go, Saturn, almost due south of us. We could shoot Saturn at 181 degrees and 49 degrees, 16 minutes of altitude. We could take that shot, it'd be perfect. So, this is a level of realism that most people, or some people at least, may not even care about. I'm just making you aware that it's there. As we already saw, you can shoot any azimuth and elevation you want and get a useful line of position from it with this Sextant gauge. But if you want to add that extra touch of realism, plan to fly at night, or plan to fly during the day, but get your sun angle here, and only shoot what's available. Let's make it daytime. Get data. Now, of course, the sun is the first thing that's up here, okay? Here's the azimuth you'd shoot it at, rounded to 74 degrees, and it's at 23 degrees and 8 minutes above the horizon. And you'll notice the moon's still visible at this point, so it'd be fair enough to take a moon shot at the same time. Venus. Is Venus visible? Probably not in the middle of the day. And we know we're not going to see any of the stars, so you can discount those. Only use what's available, and you'll quickly get an appreciation for some of the nuances of what a navigator really had to deal with here. And the very last thing I'll tell you about this gauge is that it simulates not being able to take a shot in the clouds by when you take the shot and the viewfinder opens, it'll just be covered in clouds. You won't be able to see anything. So there will be times when you're trying to get a shot and you'll have to wait until you get a break in the clouds. That's a cool feature, I think. That's definitely some added realism, because obviously it would be a factor in real life. The only thing to be aware of is that when the Sextant gauge thinks you're in the clouds, doesn't always line up with what the visuals out the window tell you when you're in the clouds. Okay, so when you're in an area where there's lots of clouds and you're in and out of the clouds, you can count on the Sextant gauge not allowing you to take a shot because you're in the clouds occasionally, but those time periods will not always line up with when you think you're in the clouds. but the ultimate result is the same. You just have to keep trying until you can get a shot, and if it's too far down the road, you have to advance your line of position backwards in time based on your ground speed. And again, now we're getting into dead reckoning stuff, and this isn't about dead reckoning. But that's an overview of the Sextant gauge, and I think I got babbling a little bit at the end there. That's where my lesson plan stopped, and I just started making it up as I went. But you know, I encourage you guys to try this out. If you like classic airplanes, this really adds another dimension to it. So look up a primer on dead reckoning, make yourself up a little flight plan, head out across the ocean, take some star shots, see if you can hit an island. It's pretty cool. I hope this helped somebody, and hey, listen, if you've listened to this and you know more about it than me, which is entirely possible, throw some comments in, correcting everything I've said that's wrong. We can all learn from it. Thanks, guys. Have a good one.